You can see the screen, right? Arun?
Yeah, it's visible.
Okay. So guys, what I would like to do today is to go through some optimization techniques, at least in data sciences. Um, this will be a class that will go a little bit slowly. I just want to make sure I cover all the topics. Uh, the unfortunate part is that it will be a bit of an overview. If you do wish to do a deep dive into any one of these techniques, I would heartily recommend you to so for the first two techniques, those are more standard, those are a little more old school, have been around for 20, 30 years. So you can probably do a lot of YouTube to understand that. The one for the last one, which is deep learning methods, my recommendation there would be to probably go through the Stanford courses. Stanford has done a lot of work, deep learning, reinforcement learning, which is going to be optimization for you, and you can definitely read that up. Some of the nuances in terms of the math behind it, which is quite intuitive, and the kind of exist underlying that. With that, I'll start off. So we have optimization in three different techniques that will be discussed today. The linear systems, which is linear programming, genetic programming, and deep learning systems. Just a brief background. Bachelor's from Delhi, master's in computer science from University of Southern California. That was, it seems like a generation ago, a long time ago. I came back to India. I did my MBA right off when I landed here. Did 6 years in finance, 2 years in New York. I think about 4 years in India, 2 years in Bombay, 2 years in Delhi, 6 years in computer science. Microsoft recently in 24/7.ai, and kind of handle fraud and data sciences for Cabbage, which is basically an online lending startup. Their headquarters are in Canada, and they have some stuff out here in Bangalore and in New York. Okay. All right. So what's optimization? We all learn is linear regression. You tend to basically fit a line over all the basic data points which are available as observations, and you try to fit it with minimization of an error. The and what you would see in data sciences a lot is optimization on a cost function. The cost function, for example, in the linear regression is the sum of square errors of the difference between the line and the actual point which it's trying to fit on. So when you try to minimize that overall cost, a quadratic function, you end up with the straight line which is passing through, trying to do a best fit. So optimization is just an extension of that. You're basically trying to optimize a cost function. You may not be trying to fit a linear function or a non-linear function or a classification problem, but underlying mechanics still remain the same. You are trying to use a cost function in order to optimize a particular objective, which could be, in the most advanced cases for now, autonomous driving of a car. You're trying to make sure that the car reaches from point A to hit or without breaking any legal rules. That would be an problem, which is also trying to do minimization of a cost function. It's trying to learn its environment based on the environment where it is in, where it currently situated, at which point of time it is, and so forth and so forth. But the underlying math, the underlying structure, the problem remains the same. Okay, so let's start with the first one, and just to give us understanding of the situation. So basically, we have an optimization function called z, in this case, which has a number of attributes which can change that parameter. The most simplest example, um, let's say there's a band, and the band is trying to make a lot of money for itself. So how many concert halls it's playing at, how many how many records they put out, how many followers they have on Facebook, etc. All these things can lead to optimization of the money that they're making as a band. But they are obviously subject to constraints, which are G1, G2, G3, so forth. There's only 24 hours in a day, so you can only do, let's say, two concerts per day. There's only 365 days in a month, in a year, so you can only do, let's say, maybe three albums in a year without sounding too much, and so forth and so forth. So these are all constraints which can exist in the real world as well as in the mathematical world. So the optimization function has to optimize the problem within those constraints. Linear programming tends to make the assumption that this thing that we were just discussing is a linear problem. So the function f is a linear function. The constraint G to G3 are all linear constraints. So how does that work? You basically have an objective function, which is the f we were discussing. So in this case, let's say it's x1 and x2. How do we define that? Let's say x1 is the number of machines that are existing in, and x2 is the second machine which is existing in the factory. The factory is just trying to optimize, how many hours do I need to run x1, how many hours do I need to run x2, so that overall I the most amount of profit. So that's 450 into x1. So anytime, any hour that x1 is run, they make like 450 rupees. Or anytime that x2 is run for 1 hour, that's 300 rupees, right? So they're just trying to optimize that. Unfortunately, there's linear constraints which are that, which is basically shown by these lines out here, the lines which are intersecting each other. So for example, x1 may say that, I can only run for such amount of time. After that, I have to cool down. I cannot be running 24 hours a day. There can be another constraint on x2. Combined constraint on x1 plus x2 that there's only 24 hours a day. So there's a limitation as to how many hours they can run overall, right? So all these things intersect with each other, which can lead to something called as corner points in a linear programming problem. And essentially what happens is that the optimization function just has to go through the corners at any point of time. So basically you have 1, 2, 3, 4, 5. You have 5 corner points out there. You would just run the optimization, the 5 points to find the one which has the max value. And the reasoning behind that is any area in the function, any area out here which is a viable solution will be beaten by one of these 5 corner points. So it's the nature of these constrained optimization solutions that at least the linear optimization solutions that the global maxima will lie on one of these extremities. So that's the main way in which optimization works, linear optimization. But you can have some variations on top. And just to give an example, for the last 20-30 years, linear optimization has been the gold standard for a lot of problems. Aircraft scheduling, it has handled truck scheduling within factories. It's there for a lot of other problems that if you search online, you'll be just surprised as to how many linear optimization solutions exist out there. In fact, it's even part of Microsoft Excel. Microsoft Excel has a solution called Solver. You can use it there, and it basically does linear optimization for you. So what other things can exist on top of linear optimization? For example, you may not just have one single factory machine at this point. You may have two available for X1, so that may change. Your unit profit may change. So, for example, X1 may come up with a better version. So the manufacturer for X1 may come up with a X1 dash, and that X1 dash is no longer providing 450 profit; it's providing 500 rupees profit. So those coefficients may change as well, which can change the nature of this geography, the nature of this geometry. So what is one of those scenarios? So shadow price is actually the way in which we handle this kind of ambiguity and this kind of nature. Out here, z is, if you remember still, the objective function. So what it says out here is that, let's say we change the constraint from for one of these lines, one of these constraints from M2, which was the dotted line, to M2 dash. And that basically increases the function by a delta amount, which is also the shadow price for that particular constraint. What you're saying is that as the person moves from M2 to M2 dash, there is a delta increase in the potential profit that may exist from that capacity change in M2. So that's one of the sensitivity calculations that can be done. And obviously, if there are some questions there, we can either discuss it after this, and or you can obviously search in YouTube and get those answers. Further readings within linear programming are quadratic, integer, and binary programming. These are just small variations on top of linear programming. Integer programming, for example, says that out here in the green area, the viable solutions can only exist for 1, 2, 3, 4. They cannot exist for 4.3, 2.3, and so forth. So there's ways to handle that. It's a small on top of linear programming. Quadratic programming can basically say that it's not a linear function, it's a quadratic function. Binary programming is essentially that the x1, x2 can only have a 0, 1 value on top of it. That's another variation that can exist. You just have to change the structure of the problem to make that work. A classic example of binary programming would be that I have 10 workers and I want to schedule them across 7 days in a factory. How would I do the scheduling for each one of them, given that each one of them has different productivity and different ability to execute some task and try to optimize that particular problem. So each person is a 0, 1, either they're there in the factory or not in the factory on that day. So let me just take a sip of water and we can start off with the next one. Okay, so the next one is genetic programming. That's a little more so the previous one was a little more mathematical. This one is very intuitive. So genetic programming is, Darwin used to say, it's a survival of the fittest. This picture, by the way, is a good example of how evolved over the years, right? In the centuries that have had tigers, we have had two different strains of tigers. One is the white tiger, the other one is the usual savanna tiger that exists within India as well as in Africa. The nature of this picture is the ability to survive within the surroundings. Sorry, I'm getting an echo here. Okay. The nature of okay, I lost my, okay. So the nature of the right side is that the tiger on the right side is adapt to its surroundings and thus has been able to survive its surroundings better than the one on the left. It's easier to distinguish the white tiger against its surroundings out here, but it's not so easy to distinguish where the tiger starts on the right hand side versus its surroundings, thereby its ability to evade capture, its ability to hunt better prey, and so forth and so forth. Okay, so how does evolution work? Not all members can survive. So you saw the tigers on the left side on the previous slide, right? Only some of them can actually earn the ability to eat lunch, and the others would be just mutations, which basically just either get eaten or are not able to survive. So the strong ones, they attract, they mate with other members of the species, and they right. Offsprings can go either way. They can either be better than the parents, or they can, in some cases be worse off than the parents. Overall, the species overall develops, and that's been the progress of nature. Nature has always worked like that. It's a slow evolution process. It doesn't work very quickly. But obviously, when you're working with computers and multiprocessors, you can work very quickly. So it's optimization. So you start with random solutions. So for example, let's say I was looking at problem from the previous discussions, right? I could start with all kind of random solutions which are fitting within the constraint space, within that blue shaded area. But I don't know which one is the right solution. So how do I work with that? So you kill off the weak ones, which are not leading to the highest optimization. So the ones which are leading to optimizations in terms of numbers, those are the ones you keep for the next epoch, or the next species, or that epoch is the one which gets to create offsprings. They mutate with each other, they create offsprings, which can lead to perhaps a better generation for the next epoch to be trained on, which is essentially the nature of the optimization problem via genetics. Train for enough epochs, the idea would be that eventually the species would stabilize, it will reach its global optimum, and you would global optimum for the optimization that you're trying to achieve. And even though it's a very straightforward idea taken from nature, it tends to do really well for some of the problems that we face in mathematics as well as in computer science. So I don't know why am I hang on, just give me a sec. All right. So genetic problem at a glance. We create a schema with possible solutions, bit-byte format. They are random solutions, like I said, and you create new ones from them based on some exchange mechanism. So you only create the new ones from the ones which are performing better. So like I said, the initial population is better off, or they will be excluded from the next epoch. So you'd only take, let's say, the top 50 percentile of the species for the next generation of the species, and so forth and so forth. So when you create new ones from them, you can create an exchange mechanism. And there's definitely some papers out there, or there's some very standard mechanisms out there for genetic programming to create offsprings from each other. You could swap bytes. So if it's a 0-1 type of stream, you can just replace some of the 0-1s between the two, so male, female, in order to create a new offspring which is completely different from male and female, and so forth and so forth. So you continue with these two last steps again and again till the solution is stable and optimized. So some of the sample problems which are solved are knapsack, polynomial fit, traveling salesman problem, which is actually an NP hard problem. So if you try to solve traveling salesman problem via algorithms which are not genetic or which are not randomized, like you would not be able to solve them with a normal machine. Theoretically there is no. It's a polynomial raised to the power n. Hence, the nature of the problem is such that it's difficult to solve in a deterministic fashion. However, with genetic algorithms, because of the nature that it's trying to create offsprings and so forth, it's able to solve that in a fixed amount of time, which is amazing. So portfolio allocation as well. It used to be a system where people used to use genetic algorithms for portfolio allocation. Although to be said, it's not used as much in that space anymore. Reinforcement learning, which is the last step we'll discuss today. Just give me a second. Okay, so this is where deep learning starts coming in. All right, let's get started. So what does reinforcement learning solve? And this is a classic problem. You basically have a problem where there's an agent, which is a computer agent, a neural network agent, who's trying to interact with an environment, and they are getting rewards based on the kind of actions that are taken. So I don't know if how many of you have seen this, but a lot of work that has been done in reinforcement learning in the last 3 to 4 years has been based in computer games. Classic example has been the Google's DeepMind system beating AlphaGo. Essentially, it's a computer agent. It's looking at the environment, which is a Go board or a computer game, like the screenshots which have been shown here below. Those Computer games actually are analyzed by the neural agent at through different algorithms. So we'll briefly discuss the algorithms which exist, and they try to take an optimal action which will give them the highest amount of reward and allow them to either complete the game successfully or not complete the game successfully. Their aim is to maximize their reward, and as long as the reward structure has been set up properly in mathematics, as well as in the neural network system, they will try to maximize that reward by any means necessary via the neural network. Okay. So, in detail, you have an environment which, let's say, for purpose of explanation, we have an environment which is, let's say, a computer game. You are a joystick or a person or a neural network agent, which can take multiple actions. So that can move between left, right, top, diagonally left, diagonally right, right? And those are the kind of actions you have. Each one of those actions, given where you are, can actually maximize or minimize your reward. It's a little bit of a tough situation because you are currently in a state, right? And you have to decide about how to maximize your reward, which is maybe 200 steps away. So it's not an easy problem to solve because you are at t equal to 0, you're trying to maximize your reward at time t equal to 200, which is the nature of this problem. So I'll give some mathematical rigor to it so that we can understand it a little better. The essential idea would be that with the action that you create, that you take, you basically shift between states. So currently you're in state S naught. With that action, you could move to state S1, and after that, you can move to state S2 and so forth, which can also increase the chances of you getting a reward. The reward could be R1 plus R2 plus R3 plus R4 and so forth. It could also be a discounted rate on top of the future rewards. So the future rewards could be extending into 200 steps from current point, but you want to make sure that you give high priority for the current rewards versus the future rewards. So you can have a slight discount on the future rewards as you've progressed further into the future. So there are nuances both from financial structures, the way finance tends to work with cash flows and so forth, and that extending itself into the neural network domain. So the typical place where people start learning about reinforcement learning is the cartpole problem. This is just an example of an environment. So there's an environment where there's a cart with a pole. By nature, there's zero friction out here, which is why it stabilize this particular ball on top of the pole. And the intention is to move this cart left or right, and that's the kind of the agent can take. Tell which direction I have to move in and what is the acceleration I have to move in. And based on that, the force will force this pole to either move left or right. So the intention is that this pole will continue to oscillate around the vertical point, and the more time you spend on making sure that this particular pole doesn't drop, is the more maximum reward that you take. So out here, in this particular problem, the reward has been structured as the amount of time the pole is upright, and that is basically the structure, the way in the reward function has been set up. Action, as it has been said, is a horizontal force. The state is the current angle, the angular speed of the pole, the position where it is in, and any horizontal velocity that you already have on the cart. And the objective is to balance the pole. All right. So a problem like the one which we have discussed earlier, this one as well as the video games, those are all something that we can discuss through Markov decision processes. So each one of them has been, in order to mathematically represent and to solve for these kind of problems, we call them as Markov problem sets. And the nature of the Markov problem set is quite simple. The current is decided the previous state itself, and not by previous state plus the previous state plus the previous state, and so forth and so forth. So basically, let's say there was I don't have this in front of me, but let's say we have 5 states in front of us: S0, S1, S2, S3. What I'm saying is that the Markov property says that the probability of S1 coming from S0 is only based on S0. It's not dependent on S0 plus S minus 1, and so forth and so forth. Each state is defined by the previous state, not by 2 previous states, and so forth. This was decided by a guy called Markov, who actually won the Nobel. I won the Nobel Prize. Oh yeah, he did. He did get the Markov did Nobel Prize, I think 50, 60 years ago. And it's been used in a lot of different places since then. Markov's property essentially allows a lot of difficult problems to come to a steady state, come to a balanced state, which allows for mathematical computations to take place, matrix operations to exist in a very seamless fashion, and for us to use GPUs and vectors to optimize on different problem sets. For example, Google's PageRank, the one for which they got the initial funding when they were just some unknown entity, was based on Markovian properties. The PageRank system is a matrix operation. That matrix operation stabilizes after some iterations. The iterations by them very nature, because they are a multiplication between previous state and new state, are implicitly suggesting that the PageRank algorithm is a Markovian system. So each one of them, and obviously because of that, Markov also works very well for reinforcement learning. We don't have to look at 10 different states to define the next state. We just look at the previous state. And each one of those states, which could be million and billion in nature, is defined by the set S. Actions are defined by the set A. Any rewards based on state action pair can be, given as a distribution. And the transition probability of distribution of next state given the state action pair, which is essentially the nature of Markovian properties, the transition matrix, would also be provided along with the discount factor. Discount factor would be the discount you would apply on the future rewards versus the current reward, just to make sure that there's a balance between current versus future. So at step 0, the environment samples the initial state, which is the probability of state 0. And then within that, they select an action. Based on that action, because now you have this action and state, you get a potential reward. That potential reward tells you what's the next state to take at, and so basically the cycle, the way it was mentioned out here, you basically cycle through different states based on various action, and you continue to receive your reward, and so forth and so forth. So it's a finite state automated machine. So and then obviously there's a more meta higher above learning on top of this. So if you can, for example, not only decide which state to take, but also decide on a policy that whenever I'm in this situation, I have a policy that I will take this action versus that action. Then you're not deciding states, you're deciding actions. So that's a slightly higher level understanding of the problem set, which is called as policy gradient problems. So policy is defined by pi in such cases. So this is just a mathematical representation of the problem, and this representation is used in 20 different ways in the reinforcement learning ecosystem, with different algorithms trying to attack either the policy or the state problem. They either try to optimize which state to take, or they try to optimize which policy to take. By nature, I haven't mentioned it in the slides, the policy action, because it's a more meta problem, it's higher above, it requires more training data versus the state problem. The problem is that the state problem can get out of hand in cases which are multidimensional, such as a car moving through a lot of different obstacles. That would not be handled by a state problem, because the states would be in zillions, right? But a policy would be a straightforward thing. The way a human behaves, a human would try not to hit the old lady on the road. It will not try to hit the passing cars and so forth. So there's these intrinsic policies that have been built in by the humans. So a policy gradient problem, a solution to the problem would be the more appropriate thing out there. And yeah, like the mathematical representation says, a policy pi is trying to maximize the cumulative discounted reward for that particular problem set. All right, let's set it to, okay, great. So an optimal policy, we have a negative reward for any transition, right? So let's say a person is in the white boxes, any one of the white boxes, and we want them to go to any one of the states, which are basically the stars. Any step that you take is a negative reward. Any directly the positive reward. So essentially, you're trying to tell the agent that, hey, you need to get to one of these terminal states at the quickest way possible. So the policy will try to understand that, okay, these are the kind of constraints that have been placed on me, which is again a refresh back to the previous constraint problems that we were talking about in the beginning of this masterclass. That would be the kind of constraint they would work with, and the reinforcement system will learn on top of that. So a simple Markovian problem, which doesn't have reinforcement, which is not having any policy, it's just a random policy, will try to go everywhere. And it will obviously not have any understanding of the problem set. But an optimal policy after training, with sufficient training, would be able to understand that I can move either way. When I'm here, I need to move up and so forth and so forth. Even though you're currently in a state out here, the policy would be the arrows, the blue arrows that would be learned. That whenever I'm in a position like this, I need to learn the blue stuff rather than the white stuff, white boxes. That would be more of a state problem solution. Oh boy, let me see. Okay, nope. Okay, so I think this is just a copy of the previous slide that we took. And coming to this whole area of reinforcement, and this is kind of the live slide that I'll be discussing today. So there is two ways to think about this, and imitation is another one which has just recently come up. And to be honest, I'm also learning that right now, so I don't have much data on that. But the two main ways in which work has been done in the last few years on reinforcement has been the value optimization. You're basically trying to see these states and you're trying to maximize the value based on the states. Um, um, Jesus, my. Okay, here we go. So those can include the deep Q network. This is the one which actually was used for some of the Atari games by Google DeepMind. It's also different versions of this were also used for the AlphaGo system. This works well for two-dimensional systems, for two-dimensional games, but policy gradient and actor critic problems, which one can read about later, combination of deep and policy gradient in some ways, those are the ones which are meant for more generic and abstract. The only challenge is that policy optimization requires more data to work on and to optimize on. And yeah, we're down to questions now. Let me take a sip of water, and I guess I can stop talking now. So, opening to questions.